General things. The final for our class is going to be on Wednesday, the 15th of June. And its time slot is 12 to 3 p.m. And then you get an extra 30 minutes because your entire final is going to be as a PDF in Canvas. And you're going to be writing all the working that goes with it. And you're going to upload it into the assignment, which will be called something like upload your working to the final exam here. Right? And when you get to look at Canvas on the day of the final, there'll only be one module that you'll see. Everything else will have disappeared. And that will have obviously the test in it, the assignment for uploading. It will have all the Desmos and GeoBra software that you might want to use from time to time on some of your questions. And that's all. And everything in WebAssign will have disappeared on the day of your final. But up until that day, like up until the Tuesday, it'll be there. Now, a little bit different format for this class, but that's fine. There's only going to be one thing, and it's going to be 15 questions. And it's only going to be on what I call section 2 questions, which is basically no multiple choice. And these 15 questions are going to be worth, on average, 20 points. Because the final adds up to 300 points. Now you will know, because by Sunday midnight, you'll have finished everything that you possibly can, and I will be busily working on grading that sometime during Monday and Tuesday. And so before midnight Monday, probably, I'll just do a longer. I'll be sending out your report, and your final report will tell you everything that you've done, because the course will have finished by then. And it will also tell you how many points you need out of 300 to get a 2.0 and pass the class, or a 3.0 or a 4.0. And that'll give you an idea of your goal, what you want to get. Now, although I said there are 15 questions worth 20 points, and that is true, that's on average, but some will be 15 and some will be 25, because you know, some of the really big questions, you deserve more points because there's a lot more work in them. This isn't written in stone, but roughly 60-40. And what do I mean by that? 60% of the questions roughly are going to be from the second half. So that's basically weeks 5 to 10. And this is going to be on the first half, right? Weeks 1 to 5. So up to the midterm, 40% of the points are going to be from there. Stuff you've done in the last 5 weeks is going to be 60%. So there's more weighting on the later stuff, right? Because you've already been tested a fair amount on the midterm on this stuff, right? Any other questions about the, general questions about the final? Am I doing that good a job? I've told you everything you need to know. Anything? Okay, you are allowed to use notes. You're allowed to use your TI-84 calculator. You are not allowed to do online software that solves problems for you. You're not allowed to phone a friend. You're not allowed to cheat, basically. On the day of the final, there'll be a single Zoom link, not the class link, a new one, and you'll find it in that module that will probably be called Final Exam Information. That's what I'll probably call that module. That module won't even be up and running till the weekend once I've got the final done. And then I'll just put the final in there and hide it. And then when you come in, I'll make it visible. That's the easiest way for me to do it. So you're going to be, I guess that's everything. I'm looking for questions then. Pick a topic, pick a question.
Going to be ordered based on
chronologically?
Yeah.
Yes. So the first question you will get will probably be, I'm looking at my list here. Yeah, it'll be probably something to do with partial derivatives. But don't you do partial derivatives all over the place? So I might not even give you a question on that, because I know I'm going to ask it when you have to do the divergence theorem, right? Don't you have to do partial derivatives to do that guy, right? So there are some things that are less likely to be chosen because of that, but it will be in chronological order. And so your last question will be in the divergence theorem, won't it? Probably. That's the last thing we did. Stokes theorem. Some of the really horrible big questions, and I'm thinking here just off the top of my head, do you know the ones where you have to do the centre of mass, and if you had to do all X bar and Y bar, or God forbid, X bar, Y bar, and Z bar, wouldn't that take you an awful lot of time if I asked you for the whole set? But I could just ask you for X bar. Right, just ask for one piece of it. That would just workload a fair amount, wouldn't it? Because you only need to do pieces of the puzzle. And if you can do that, I know you could do the whole thing because you just do it 2 more times, right? So it doesn't mean that the centre of mass question is not going to appear. It just means if it does appear, I won't ask you the whole thing, unless it's symmetric, right? Unless all 3 of them are the same, right? In which case you only do it once and then duplicate the other 2. Right, next question.
Could you do a max min saddle point question?
Sure. Good place to start. I'll put some in my. Do you recognize this, guys? It's vectors from 142, which was one of my earlier classes. Right, so we're doing max min saddle point. It's not a good idea for me to make up a question. So if you bear with me just for a moment, I'll go into that section and just use one of theirs, just less. Otherwise, you end up with some really weird combinations. Let's see, I should be able to go in there and then just look at future, past, there we go. So the max min saddle point is 264. No, that's not 260, that's a class. It's in 14.7 if you want to find more of your own. Yeah, let's pick a pretty standard one, which would be a polynomial, because most of them are. Let's pick one that comes out with nice numbers. Be cool. Okay. Nah, that's too easy. Let's pick something a little bit harder than that one. Yeah, same. Try to find one that's reasonable. Well, this one's reasonable. Okay. So you're given a function, in this case, 2x cubed, take away 6x plus 6xy squared. That would essentially be a surface, because if you think about that, that's sometimes called z. So here is our function, and we're being asked to find local max, local min, or saddle points, or saddle points. So you start by finding the partial derivative with respect to x. I get that. And you find the partial derivative with respect to y. Well, that gets you nothing. That gets you none. Make sure I haven't written anything down. And with respect to y, this guy gets you 12xy. And so these two are going to get you the critical numbers. Critical numbers are the values of x and y where these guys are 0 at the same time. So I'll call this equation 1 and I'll call this equation 2. So if you do when is that equal to 0, you are trying to solve when is 12xy equal to 0. And that ends up being x equals 0 is one possibility, and y equals 0 is another possibility. Are we good with that? Now, when x equals 0, I need to go over here and I need to find out when is that equal to 0 when x is equal to 0. So I'm going to take the partial derivative with respect to x. I'm going to make x equal 0 and see what we get. So I have a 6x squared, take away 6x, plus a 6y squared, and it's going to equal to 0. But I know x is 0. And so, oh, there we go, that's better. So I know that y is plus or minus 1. So I have some critical points. I have a 0x with a 1. I have a 0x with a -1, right? So they count as two possible critical numbers. And I got them by using x equals 0. Now, the other possibility could be that y is 0. Well, if you go up to this guy, and you make y 0, and you go looking for what will x be equal to in that situation, it's almost a carbon copy of the one I just did a minute ago. You're going to get that. So that means I've got a 1, 0, and I've got a -1, 0. So there are essentially 4 critical points where this function, right, could be a local max, could be a local min, could be, for all intents and purposes, it probably will be, right, a saddle point, at least in one location. So there's a guy that you use to test for maximums, minimums, and what are called saddle points, which are the weird ones. And this guy is called D, and it's f of xx, put brackets for emphasis, f of yy, take away f of xy squared. Now you evaluate this guy, and depending on certain combinations of things being positive and things being negative, you will get a local max, a local min, or you will get a saddle point. Okay. What value between these two? Because we don't care the number, just if it's plus or minus. What value, which one of these two gives you a saddle point?
Less than 0.
Okay. Now, if it's greater than 0, the guy that matters after that is what the value of the second derivative of x is. So you can actually do it for the y's as well, to be honest, but we'll do it with x's. What the second derivative of x is. If it's 0, you get one thing. If it's less than 0, you get another. Okay. Is that a local max or a local min? What does that guy get you?
Max?
It does. What does this get you? Gets you a min. Okay, so that's the test. Let's go back to our original function, just here, and we have to find its second derivative with respect to x, which looks like it's 12x. That's not much use. Its second derivative with respect to y is 12x. And that guy. And if you take this and you do it with respect to y, nothing, you get 12y. Okay, kind of boring, but that works. Now, every single one of my 4 guys, 1, 2, 3, 4. Let's see what 0, 1 gets me. Well, D is that guy evaluated at 0, which is 0, times that guy divided at 0 is 0, times that guy at 1 is 12. Would you agree that number is a negative number, right? D is negative. That means saddle point. Okay, let's look at the other one. 0, -1. You get 0 times 0, take away 12 times -1, which is that guy, and you get post 12, but okay. A little bit.
It should be squared, right?
Oh, squared, thank you. God in Himmel. There. So it still ends up being negative. Wonder why I've messed up. Just it's in the formula. Why did I miss that? It's there. Okay, so another saddle point. I have 2 other test points. Right, so I've got 1, 0 to check out and -1, 0 to check out. So what's D going to be? Second derivative. Oh, here we are. That guy is going to be 12. Second derivative, should put them up here. That's better. And 12 times nothing. Ooh. What have I done? Oh, God in Himmel. FYY is also 12. Right, 12 times 1, 12 times 1. I'm scanning over here. Take away this guy, which happens to be nothing squared. So you get 144, which is good. And I need to know what the value of this guy is at that point. It's 12 times x, it's 12 times 1, which is positive. And since it's positive, that means we have a local minimum. So I now know that at 1, 0, we have a local minimum. And can you trust me that if you do this one here, you end up with a local maximum? And we already know that at these 2 places, you have a saddle point.
Would it be a local maximum because the f of x is greater than 0?
If it's greater than 0, it's a local minimum, which sounds back to front, but that's the way it is. Have you ever done what's called the second derivative test? Where if the second derivative is greater than 0, it means it's concave up, and therefore it's a minimum. You remember doing that in Calc 1?
Yeah.
That's essentially what this is saying, right? So if that guy is greater than 0, you've got a minimum. And if this guy is less than 0, you have a maximum. Do you see, it looks counterintuitive, but that's the order it is in.
Yeah, I guess you just miswrote it then.
Oh, that could be true. What did I get them back to front?
Back at the, whenever you're writing out the formula for it.
On the left page.
Over here? No, these 2 are saddle points, so these are fine.
Yeah, no, but
So where did I screw up?
Up?
Oh, up here.
Yeah, yeah.
Ah,
okay, thank you.
Gotcha. There we go. Second derivative is greater than 0, you have a minimum. Second derivative with respect to x is less than 0, you have a maximum. And if D happens to be less than 0, you have a saddle point. If it is greater than 0, it's going to be one of these 2. The only time you have a problem is that D could be equal to 0. Could you imagine a certain combination where everything disappears? In that case, the test is inconclusive. If you had plugged the original polynomial which I believe is this guy here, if you'd plug that into GeoBra, you might be able to verify everything I just said by saying, oh yeah, I can see the max, I can see them in, and I can see the saddle points. Don't really have time to set up GeoBra, but that's what you could do.
Mr. Robertson, I have a question about that one.
Yes.
Was for the coordinates -1, 0,
Mhm.
wasn't it also a local minimum?
I'll check it again. The -1, 0, we are going to find this guy times this guy, take away this guy squared, and this guy was 12x, and this guy was also 12x, and this guy, I believe, was 12y, right? So let's check it out. If you plug in -1, oh, so you get -12 times -12, take away nothing, you get 144, take away 0, and that makes this guy another local minimum. Is that right? Yes. Looks strange, looks wrong. How could you get 2 local minimums? Well, you could have like that, like a wave shape. But how would they meet? Well, I guess they could meet in a saddle point. Yeah, I guess they could do that. Right, anyway, check out my calculations. The theory is correct, but you know me being untidy, I may have put a plus where a minus should be. But the theory is, if you get your D less than 0, it's a saddle point. If you get it greater than 0, it's a max or a min. Go looking for the value of fxx. If it is positive, it's a minimum, and if it's negative, it's a maximum. And I'm just checking what they say it is. Yep, they have saddle points at the right place. Ah. The second derivative is 12 times x. At the point -1, 0, isn't that 12 times -1, which is -12? So it was a maximum after all, Maggie.
Okay, thank
So
you.
I was right the first time. I wish I hadn't changed it. But I'm not used to being wrong. I tend to assume that I am wrong. And if you put in the other point, which was this one, the second derivative is 12 times 1, which is positive 12, which is why that is a minimum. And the other two, D was less than 0. That's why they were saddle points. Okay, have we got another topic or another question?
I have one.
Go for it. What you got, David?
It's actually number 9 on the homework.
Okay, that works. You want to hold on a minute? I'll go hunting for it. Number 9 in, well, are we talking the last homework or the last topic?
Homework,
Right.
16.9.
Gotcha. I have to go into current or recent to find that. And question 9.
Yeah, I quadruple checked my work and I still getting the same answer. So wondering what I'm doing wrong.
Well, let me look at yours in particular. I can do the question at the same time, David. It looks like most people who've done them came out good, but there is one that's causing. Mia, it looks like you had the same issue with question 9.
Yes, I did. I did the problem multiple times and I still kept getting the same answer and it was wrong. So then I tried the negative version of it and then that was also wrong. I only
So
put it
it
in
wasn't the
once,
plus
so.
minus then that was the issue, which is the easy one to fix.
Yeah.
Okay. So
And I
I'm going to,
followed the same steps as we did in class too. So
right,
I'm-
so let's
I'm-
figure out what went wrong.
I'm
I-
wondering if they do that weird, they double it and then they get rid of something. I'm just wondering if they're doing that. They've done that before.
Oh, it's some kind of variation to reduce the workload kind of thing.
Yeah, I'm wondering if they do that, but it could be they just did something else weird. I don't know.
Weird is possible. I'm clicking on this one as we speak. And I'll put on their solution to it.
So
So-
I did the I think what the issue was the bounds that we set up were incorrect because I did it with
Okay,
a different version of bounds and I got the answer correctly because the first time the way that we did it in class that wasn't working. So I tried it a different way and that worked. So I think we might have messed up the bounds for
it's possible. So let
Okay.
me set up the question again. It looks like that. That's basically it. And they have a picture of a kind of curved wedge, right? And so the bounds that we should have got, hopefully it's something simple. If you rearrange this guy, you get z is 1 minus x and z equals 0. I'm pretty comfortable that that would be one of ours. Let's see what they did. Yet they are agreeing with us. And on the second one, that's where the difference happened. You've got x equals y squared. And the bounds that they have for it are they have x. Let's try that again. They have x equals y squared to 1. And why did they do that? Okay, if I draw the x and y, if you do x equals y squared, it goes like that. And then it gets cut at 1. Oh, that was to do with the orientation. Right, so if you do a horizontal guy, you're going to be going from this guy to that guy. So x is equal to 1 to y squared. That's what it was. Is that the bounds you set it up with?
yeah, that's what I ended up doing.
Right. So when I did it, I looked at this guy and I made those the bounds. Can you see? It's a plus 1 minus 1. That's where it went wrong. So all you need to do is make sure you go from 1 to y squared and you finish with y going from -1, which is down here, to +1. So it's a type 2. You're doing the shape this way. I guess if you look at the picture, you can kind of see it is something like that. And then there's a straight line going. And this straight line is through the y-axis, and that guy there is at 1. And then the x-axis, sorry, the other axis is like that. And so that is the shape. And it's just the orientation that's a little bit weird. So if you take that and you turn it, that's what it looks like. So it was just setting up the limits of integration. Are we good now?
Yeah,
Okay. The fact that other people have got it to work, I mean, it's a pretty good sign that that's all we need to fix. Okay, what's our next question? Anything?
Can we do a center of mass problem?
I can certainly try. They're long, so I'll see if I can find a short one. They're all over the place. It's hard to tell where one is because they're not a section on them. They just kind of appear at the end of lots of different questions. So let's see if I can find one in Green's theorem. Is there a centre of mass in Green's theorem? Yes, there is. Which one? Well, they gave you the formula, but I guess that's the best we can do. I don't know if that's really a centre of mass question. I'll show you the ones I'm talking about. If they give you a formula, it's not really the same thing as doing it from scratch. But here's one. Here is the region. X bar is this closed line integral, and Y bar is this closed interval. And they've got the thing here, and then they get a solution. So I don't think that's a good choice. Let's see if I can find one. Where else would we have those? Not in this surface. Maybe here. Is that where I just came from? No, just videos, Stokes. No, go further back. Maybe here. Go. Nothing interesting. Ah, got one. Okay. No, it's got the same blinking formula. Triple integrals have a possibility. Double integrals for sure. Try that one. Typically should be at the end if we have one.
I think you might find some in 15.4 applications.
Fifth. Oh, that sounds like a sensible place to put them. Yep, we got some. Okay. Okay, I got one here. What does it look like? So you're going to have to find a centre of mass of some region D. And it has a density function. Sometimes the density function is just a constant K. In this case, it's a kind of 7 ky. It just basically means that at the y coordinate, the density keeps changing. So it's like going vertically upwards, it's getting heavier. And you've got a region D, and D in this case is this guy, and y equals 0. So first thing I'm going to do is do a sketch of the region to make sure that I get the real D. Right, 1 minus x squared is pretty easy to do. And y equals 0 is pretty easy to do. So this one came out. There's the region D. So once we've had, oh, and by the way, -1 to 1. First thing we're going to calculate is the mass. And the mass is basically just going to be the integral. In this case, well, if we're doing a single value, we're going to be doing, going to be a double integral, and we are going to be doing, I think a type 1 here. So I'm going to be doing x goes from 1 to -1, and y is going to go from 0 to this guy, which is 1 minus x squared. So it's going to be from x equals -1 to x equals 1, and from y equals 0 to y equals 1 minus x squared. And then what goes in here is the density function. In this case, it's a dy, a dx. So we're going to be doing this double integral of 7ky dy by dx. And let me cheat and find what they say it's equal to. And they say it's equal to that guy. So can you imagine doing the integral from 0 to 1 minus x squared of this guy with respect to y, and then doing it from -1 to 1 with respect to x, and we got this guy. So you find the double integral of the density function, you get this guy. Then you find two guys which are called the moments. One of them is called this guy, and the other one is called that guy. And they are going to be the same double integral, right? So it's going to be the same regions as here. So it's going to be y equals 0 to 1 minus x squared, and it's going to be x equals -1 to x equals 1. And we just have to incorporate a little bit extra. And these always look to me to be back to front, but it kind of sorts itself out. What do we multiply here when you're doing a moment around the x's?
Y.
You do a y. I don't know, does that seem back to front to you? It just seems back to front to me, right? And so in this case, it's going to be a double integral over the same limits, y times 7ky, so that's going to be 7ky squared, dy dx. And after about another, whatever, 10 minutes of whatever, you get the answer 0. Wow. Okay, that's what they say it is at 0. Now, if you want to do this one over the same limits of integration, according to them, you get 32 over 15k. It really is just slightly monotonous, isn't it? It's just a double integral with lots of polynomials plugging in things, and you get this guy. So once you've found the mass, you find the moments about x using that formula. You find the moments around y using this formula. And then you can get x bar and y bar, which is the center of mass. And you take this guy and you take this guy, and then it looks back to front again, but it works. So x bar is essentially the moments around y divided by the mass, and the moments around x divided by the mass. So if you take this guy and you divide them by the mass, which is this guy, if I got that the right way around, I think I have. It's my, yeah. That looks wrong. My next x and y. Let's check the x's in case I wrote down the wrong thing. 56. Check. My 0. My is 0. Okay. That's 0, and that's 32 over 15. Now that looks much better. Can't even write the thing down today. 0 over the mass, so that's just 0. And this one is going to be the 32 15ths k over the mass 56 15ths k. That looks much better. And that comes out, oh, the k's cancel, and you get 4/7. So there is center of mass is that